video, we will be explaining torque in a real-life application.
Force is the action that creates a change in linear motion.
For rotational motion, the same force can cause very different results.
Torque is an action that causes objects to rotate.
A torque is required to rotate an object, just as force is required to move an object in a line.
Torque is created by force, but it also depends on where the force is applied and the point about where the object rotates, which would be our fulcrum.
So when an object is in rotational equilibrium, the net torque applied to it is 0.
Rotational equilibrium is often used to determine unknown forces.
An object that is not moving is in rotational equilibrium, and it is in transitional equilibrium.
For example, if an object such as a seesaw is not rotating, you know the torque on each side is balanced.
We will be using these figures to show our real-life application of torque.
First, weigh each object and make sure you convert it into kilograms or your whole equation will be messed up. Alvin weighs 21 grams, but the measurement we would like to use would be 0.021 kilograms. Woody weighs 65 grams or 0.065 kilograms.
Okay, for torque equals force times distance. To find the force that each object is exerting on the seesaw, you do acceleration due to gravity times its mass in kilograms. For Woody, it equals 0.065 kilograms times 9.8, which gives you 0.637 newtons of force. And Alvin equals 0.021 kilograms times 9.8 meters per second squared equals 0.205 newtons that it's exerting on the seesaw.
So when trying to figure out where to put Alvin, we place x on that side of the torque equation. Woody equals 0.637 newtons, which we discovered from our earlier equation, and we multiply that by the distance he is away from the fulcrum, which is 0.1 meters. And we set that equal to how much Alvin force is, which is 0.2058 newtons, multiplied by the unknown distance, which is x. We then multiply Woody's force by the distance, which is 0.637, and we set that equal to 0.2058x. We then divide 0.2058 by Woody's force to get the total distance that Alvin should be set to have equilibrium to be 0.3095 meters away from the fulcrum.
As you see here, these objects are in equilibrium, with Woody being 10 centimeters from the fulcrum and Alvin being 30 centimeters from the fulcrum. As we got our distance that Alvin should be from the equation is 0.3095 meters.
The two objects we are using are the red Power Ranger and green alien. The red Power Ranger weighs 21 grams, which is 0.021 kilograms. And the green alien weighs 46 grams, which is 0.046 kilograms.
The red Power Ranger exerts 0.2058 newtons on the seesaw, while the green alien exerts 0.4508 newtons on the seesaw. To find the distance the red Power Ranger should be from the fulcrum, we found the torque of the green alien and then divided it by the force exerted from the red Power Ranger, giving us the distance away from the fulcrum the red Power Ranger should be, which is 0.219 meters.
Just as we used a scaled seesaw with these figures that represent people, on a larger scale, on a real seesaw, you could use these exact equations that we use to figure out how far you should be to maintain equilibrium on seesaw. As to increase torque and set it equal to each other, if you have an increase in force or an increase in distance, this will increase your overall torque.